So now we can put this all together and look at the hydrogen spectra. So now we can look at the hydrogen in all of its glory right here. Here is the wave function, big psi. It's a function of r, theta, phi, and t. And it's got the three quantum numbers, the n, the l, and the m sub l. This was my radial part right there. Remember, those were the Lejeune polynomials. Then we had the spherical harmonics, but this spherical harmonics was really made up of another normalization, Legendre polynomials, except for every place you see an x, you put in a cosine theta. Here, every place we saw an x, we put in a 2r over NA naught. There was our phi part, and then there's the energy part right there. Now, I should say, this really isn't all of it, because we haven't brought in the spin of the electron. So really, if I was going to bring in the spin of the electron, which we'll do later, but really all I'd have to do is I'd have to bring in a what? Alpha and beta. You know, if it was 1, 0, it would be in the up state. If it was 0, 1. So I have to mix. This one is a 1 by 2 along with these functions right there. But I don't want to bring that up now right here. Okay, so we just want to look at the energy spectra now. And remember, we said n was equal to the radial quantum number, which we're not going to use, plus L plus 1, where n goes from 1, 2, 3, 4. L starts at 0 and goes to n minus 1. And m sub L goes from minus L all the way to plus L in integers. So if we were to look at our energy diagram, so this is energy right here. And our lowest state would be where n equals 1. So right there, this is n equals 1. We know what that energy is. That energy is equal to minus 13.6 all over n squared. Well, if n is 1, it's just minus 13.6 eV. Okay. Now, when n is equal to 1, that means both of these two have to be 0 because n is equal to the sum of these three numbers, and we already have our 1 there. So n sub r, so this energy we have here, n sub r is equal to 0, and L is equal to 0. Okay, and we would call that and m sub L can only be one value, it can only be 0. We would call that the 1s state again, the 1s state. Okay, now if we go to the next state up right here, I'm going to just draw it right there. This is n equals 2. Now I should say there was only one state here. There was only one state, so let me put that in parentheses. There's only one state. For n equal 2, for this to equal 2, L could be, n sub r could be 0 right here. So if n, let me just write that right here. One case is n sub r equals 0. And if n sub r is 0 and that's 2, that means L is equal to 1. So this would be L equal to 1. We would call that the 2p state. The 2p state right there. And m sub L, remember, goes from minus L to plus L, so it goes from minus 1 to plus 1. So m sub L could equal 1, 0, minus 1. So there were 3 states here. So I better put in parentheses here. There are 3 states there. I'm going to put it right there. There's 3 possible states there, all with the same energy. But there's also another case. N sub r could equal 1, and then L would be 0. So let me put that still at the same energy. So that's over here. That's at nr equal to 1, and L is equal to 0. So all I did was make this one bigger and that one smaller, but n is still 2 right here. Well, since L is equal to 0, m sub L can only be 0. Remember, it goes from plus this to minus that. Okay, and we would call that the 2s state, since L equals 0. That's the 2s state, and there are just one of them right here. Well, there you got 3 states here, you got 1 state there, so there's a total of 4 states right here that all have the same energy. We would call that the degeneracy is 4. There's 4 different states. The only way I'd know which state I was in is I'd have to measure the angular momentum and the z component of the angular momentum. Get all the quantum numbers, then I know exactly what state it is. Okay, well, let's go to n equals 3 here. N equals 3. Well, n sub r could still be 0. That means that this would be 2. So you could have n sub r equals 0, L equals 2. And then m sub L goes from minus 2 to plus 2, so it could be, so m sub L could be 2, 1, 0, minus 1, minus 2. So there are 5 states here. And we would call that the 3D state, SPD. D, L equal 2 is the D state. So this would be the 3D state. Okay, and then n sub r could also be 1. So if we come over here, it's the same energy. N sub r could equal 1. Now, if this is 3, and that's 1, and there's 2, that means L is just 1. L is equal to 1. That means m sub L can be 1, 0, or minus 1. We would call that the 3p state. And we would say there are 3 states. All 3 right here. There's 3 states. Or we could say n sub r equals 2, and that could be 0, and that would give you 3. So we have another one right here. N sub r equals 2, L equals 0, and so m sub L can only be 0. There's only 1 state in that one, and we would call that the 3s state. Okay, so the total number here is 1 plus 3, that's 4, plus 5, that's 9. Well, let's try one more here. 4 state. N equals 4. Again, n sub r could equal 0. That would mean L equals 3. That means m sub L could equal 3, 2, 1, 0, minus 1, minus 2, minus 3. What's that give you? 7 states. And we would call that the 4 SPDF, F state right here, 4F state. Okay, and then we could also have NR equal to 1. Well, that means I have 1 less than L. That's L equal 2. So M sub L equals 2, 1, 0, minus 1, minus 2. This gives you 5 states. And we would call this the 4D state. Okay, and then we have out here, we can make n sub r equal 2. That means L equals 1. Or m sub L equals 1, 0, minus 1. So there are 3 states here, and we would call that the 4p state. And then one more out there, because n sub r could be 3. L equals 0. And that only gives you 1 m sub L equals 0. So there's only one state there. We would call that the 4s state. Okay, and so how many would that give us? That'd give us 4, and 5 is 9, 9 and 7 is 16. 16, okay. So by looking at these numbers, it looks like the degeneracy goes as n squared, because that just looks like an n squared. So we can say the degeneracy goes as n squared. Well, if you look at the periodic table, it actually goes as 2n squared. You know, in the first level, there's 2 of them, and so, you know, not if you put in 1 there, you only get 1. If you put in 1 there, you get 2. Well, that's because we're off by a factor of 2 because we haven't brought in the spin. The spin will bring up, remember, we have 2 possibilities, up, downs. And so that'll double everything here. Okay, now we did have some selection rules right here. We had our selection rules, I guess we'll just write them over here. Delta L is equal to 1, I guess we could say plus or minus 1, and delta M sub L could be 0 plus minus 1. So if we come over to here and look, and when we make a jump, you've got to jump down this way. You've got to lose energy to emit a photon. But you'll notice I can't jump from here to here because L was 0 and L was 0 there. You have to change L by at least 1. So that can't happen. This can happen right here. This one right here. All of them, because M sub L can change by 1, 0, or minus 1 right here. It's just that if it went from 0 state to the 0 state, it would be polarized light. If it was 1 to the 0 state, it would be circularly polarized, and this would be the other circular. But it would still emit the photon. So there's one jump right here. If we come over to here, if you want to jump to here, the only one I can jump to here from is I can jump here because L can change by 1. Or I guess I could jump over to here. L can change by 1 right here. So okay, and likewise, it looks like we could make this jump right here. Couldn't make that jump. Could make this jump right here. Now, you can't make all of these jumps because, you know, like the M sub L equals minus 1 can't go all the way to the M sub L equals 2 state because that would be a change in 3, right? It can only change by 0 or 1. So it's only some of these states are going to work right here. Same with here, when you're making this jump, you can't go from a 3 to a minus 2 or even a 3 to a 0 state. You know, you have to stay within that M sub L. Well, how do we get to this state then, right here? Well, maybe we use a different color right here. If we want to get to this state, we've got to come from a different L. I guess we could come from here. We can't go this way because you're going from 2 to 0, but we can jump down like this. We can't jump that way either. Can't go from 0 to 0. Likewise, how do we get to this one right here? Well, we can come in this way. We can't go this way because L would change by 2. We can't go this way, but I guess we could come in over here. Again, selected ones. Remember, these are a whole bunch of lines on top of each other because of the degeneracy. How do we get into this one right here? Well, let me even pick a different color here. We need to jump from an L equal 1 state right here. So at L equal 1, we could be right here. I guess we could be, that was the only one. You can only jump. Yes, that's the only one right there. Now, I should say, we can jump down 2. So, is there any higher one I can jump from here? Well, this was L equals 0. If you wanted, do you have any L equal 1? Yeah, this one right here, I should be able to jump all the way down to here because L is changing by 1. So this one is also favorable right there. Same with from here to here. That looks favorable right there. This one looks favorable right here. So there's going to be jumps like this right here. And again, from even higher up, I could come down to here. As long as L changed by 1, and within these, the M sub L changed right here. And so this will give me the whole Bohr spectra we had. We also know how long it's going to take for these things to drop from those dipole matrix elements. So this is giving us quite a bit more detail than just the Bohr model right here. We'll go into a little bit more detail on the next lecture, but this one I want to do one example problem here. Suppose we have psi is in a mixed state right here at t equals 0. So this would be so this is really r, theta, and phi. But it's in a mixed state. That's it's 4 all over 2a naught to the 3 halves times e to the minus r over a naught all over the square root of 4 pi plus a. This a, r over a naught times e to the minus r over 2a naught times minus I y, the spherical harmonic, 1, 1, plus y, 1 minus 1, plus the square root of 7, y, 1, 0. Okay, we got this mixed state. It's really a mixture of how many states? 1, 2, 3, 4 states right here. And we want to answer some questions about this, but first thing I want to do is I want to find that constant A right there. Now, instead of working with this all in terms of R's and all that stuff, I'd like to put these all in terms of my size of NLMs. I should be able to do that on the right side. Now, maybe I'll multiply this through first. Right here, I hate doing that, but we'll multiply this through. So we got 4 all over 2a naught to the 3 halves, e to the minus r over a naught all over the square root of 4 pi. So that takes care of that first term, plus this times this, 4 over 2a naught to the 3 halves, a r all over a naught, e to the minus r over 2a naught. And so I'm going to get, so that was these two multiplied together, but I'm going to get it with each, I'm going to get 3 of these, one with this term, one with that term, one with the last term. So with the first term, it's going to be a minus I here, minus I, and then I'm going to get plus, whoops, y, I still get the y, 1, 1. So that's this times that, and then we also get plus all of this without the I, 4 all over 2a naught to the 3 halves A R e to the minus r over 2a naught all over a naught y1 minus 1 plus the last term plus 4 over 2a naught to the 3 halves ar e to the minus r over 2a naught all over a naught. Probably didn't have to do this all out so much. Y 1 0. Okay, so there it is if I just multiplied it out. Now I'd like to get these in terms of the size. Now this one looks like my lowest state, the 1 0 0 state, almost. Right here. Here I wrote in the 1 0 0 state right here. So what I'm going to do is I'm going to see if I can pull that out from this equation right here. We need to pull out a naught to the 3 halves in the denominator. So if I pull that much of it out, and we also pull out the square root of pi, and we pull out the e to this right there. Those three things together is my psi 1 0 0. So this becomes 4. This is 2 to the 3 halves, so that's 2 square root of 2. This is 2. The 4's drop out. This is just 1 over the square root of 2 psi 1 0 0. Okay, so there's the first term. So that's all of this term right here. Okay, then we get minus. Now that term over there looks like an R2 state right here. See this? Why? Because I saw there was an R and there was an e to the minus r over 2. Remember, it's NA naught, and I can see it's a 2 up there. So let me see if I can pull that stuff out. Actually, instead of that, I'm gonna say this: R e to the minus. Actually, I'm gonna write it over here a little bit further. R e to the minus r over 2a naught. If I were to just look at that right there, actually, we'll divide it by the a naught. A naught. From this equation, that means that's just this right here, r over a naught e to the minus r over 2a naught. It looks like I'll just put this stuff over here, and it's r21 square root of 3, and then put that down below. So this is r21. We're going to move the square root of 3 over, and we're going to bring the 2a naught to the 3 halves on the top. 2a naught to the 3 halves. Okay, so that means that this next term is, I'm going to replace everything where I'm going to replace all of this, because there's the r over a naught e to the minus r over 2a naught. I'm going to replace it with this right here. So that becomes minus I 4 all over 2a naught to the 3 halves times my big A times all of this. Well, we'll put the square root of 3 in. Oh, we got 2a to the 3 halves, which is good. It's going to cancel the one below. 2a naught to the 3 halves. And then I'm going to get an R21. But R21 with Y10, remember that's L, M sub L. This is NL. I can combine those into my psi. That would just be the 2, 1, 1 state. Psi 2, 1, 1. N is equal to 2, L is equal to 1, just like we said. L is equal to 1, M sub L is equal to 1. Okay, and then these two canceled out right there. Okay, that'll make it a little simpler. Now, this one over here looks identical to this one. It just didn't have the minus I in it right here. That's the only difference. And this term was a minus 1 instead. So it's going to be the same thing. It's going to be plus, without the minus I, it's just going to be the 4a square root of 3 psi 2, 1 minus 1. Okay. And then the last term is, there was a square root of 7, and I didn't see it coming down here. There's a square root of 7 right there. The only difference on this last term, it's going to be exactly like this, except it has a square root of 7, and it'll be the 2, 1, 0 state, because I have the 0 up there. So we got plus 4a square root of 3 square root of 7 psi 2, 1, 0. Okay. So that's a little bit simpler right there. And now I just want to make sure that it's normalized. That means that this squared plus this squared plus this squared plus this squared has got to be 1. And solve for a. Well, this squared is just 1/2 plus this squared. The i's drop out because you're multiplying it by its complex conjugate. This would be 16a squared times 3. And this would be plus 16a squared times 3. Well, it's just doubling this, but we'll just write 16a squared times 3. And then the last term is plus 16 times a squared times 3 times 7. And that should equal 1. Okay, so we can get our a out of this. I'll bring the half over to that side. We'll just make that a half. Out of this term, I'll factor out the 16 times 3, a squared. Okay, and I'm left with 1 plus 1 plus 7. That's just 9. And that equals 1/2. Okay, and then we'll just solve for a here, divide that stuff out. So a squared is equal to 1 over 2 times 9 times 16 times 3. Okay, if I take the square root of that, a would equal, that would be a third, and that would be a fourth. So we got a 1 over 3 times 4, and then that would be the square root of 6. And so that would be 1 over 12 square root of 6, 1 over 12 square root of 6. Okay, now we know what the wave function is. So if I were to rewrite this and put in our value of a, this first term, this stays the same, 1 over the square root of 2, psi 1, 0, 0. This next term right here, we get minus I 4 square root of 3 times my a. Well, if I multiply that, 4 square root of 3 times this times 1 over 12 square root of 6. 4 over 12, that's 1/3. And square root of 3 over the square root of 6 is square root of 2 in the denominator. So it just gives me 1 over 3 square root of 2. And we're on this term, psi 211. Okay, and then this term, it still is the same thing because the numbers are still the same. I just don't have the minus I. So it's just going to be plus 1 over 3 square root of 2 psi, and that one is 2, 1 minus 1. And the last one is still the 4a square root of 3, but I have an extra square root of 7 in the numerator. So it's going to have a square root of 7 plus the square root of 7 all over 3 square root of 2 psi, and that one would be the 210. 210. Now I can check this, make sure the algebra is correct, because this squared plus this squared plus this squared plus this squared better be 1 right there. Let's just make sure it is 1. This is a half. This squared is 1, that'd be 2 times 9 is 1/18 plus 1/18. This is another 1/18. And this one right here would be a 7/18. And if I make this common denominator, put a 9 and a 9 there, this is 9/18, 10/18, 11/18, 18/18, which is 1. Okay, so it is normalized right here. Now, I could ask, what is the expectation value of the energy? Right here. Well, how many energies do we have? Well, you could only be n, it only depends on the n quantum number, and so n can only be 1, or all of these are the same, it's 2. So what do? We say so it'd be E1, E sub 1, times the probability of getting E1, which is a half, plus E2. And what's the probability? Well, if all this is 1/2, then all of that must be the other 1/2. So it's times 1/2, which is minus 13.6 times a half plus, and then E2, remember, is minus 13.6 over n squared, which would be over 4, times 1/2. Okay, I can pull out the minus 13.6 over 2, and we're left with just 1 plus a fourth, which is 5/8. So it'd be minus 13.6 times 5/8. Whatever that is. That would be the average energy right here. What about the average L? Average L, well, yeah, I'll just say L, or L squared. Or maybe we'll do L squared. Well, what can L be? Well, it could be, L can be 0 or 1. That's it right here. So, well, if it's this one, the probability of that is 1/2. But the L for this, remember, L is the square root of L times L plus 1. Since L is 0, this is times 0. Plus, all the rest has a probability of 1/2, because they all have L equal 1, times the value you could get with it. Remember, it's L squared. L squared is equal to L times L plus 1 H bar squared. When L is 1, that's 1 times 2, it's 2 H bar squared. 2 H bar squared. Okay, and plugging that in, that's just H bar squared. Okay, that would be the average. If we wanted to get the average L sub z, well, L sub z only depends on the third quantum number. For this one, it's m, remember, L sub z is equal to m sub L H bar. Well, for this one, it's 0, and for that one, it's going to be 0 also. But so on this one, we get the probability there, which is 1/2 times the value, which is 0, plus the probability of this one, which we said was 1/18, times the value, which is, that was m sub L is 1, that would just be h bar, plus the probability of this one, which is 1/18th, times m, that's minus h bar, because m sub L is minus 1. So that is minus h bar. And then the last term is, well, it's going to be 0, whatever it is, because we get a 0 there. Okay, and we can see that this is 0 and that's 0, and these two just cancel each other out, so this is just 0 right here. Well, what happens if we said, what is psi as a function of time going to be? Go back to this original thing and say, what does psi look like as a function of time? Well, we'll come back to here. What does the time part look like? The time part, remember, is e to the IE over h bar t. Well, you'll notice E only depends on the n quantum number. So all it would do is, with this term, it would put in, maybe I'll just write it on it. It would put a e to the minus ei E1 over h bar t. Okay, and then all of these other ones are all the same, and so they would just be multiplied by e to the minus IE2 over h bar t, e to the minus I2 over h bar t, e to the minus I could have factored it all out too. So these three terms right here, you would have multiplied by e to the minus IE2 over h bar t. H bar t. And we know what E1 and E2 is right there. Well, what if we measure L squared, and let's say we get, let's say we measure L squared, measure L squared on that operator, and we get 2h bar squared, and we get it equals 2h bar squared. And then we ask, what is the probability of getting LZ equal to 0? So measure this, and then it's the probability of getting LZ equal to 0. Okay, so first say we measure LZ, and we get 2h bar squared. That means that L must have been 1. So this thing, by measuring that, we just said we're collapsing it to the L equal 1 state. So that means we're collapsing it. That means this guy's getting rid of, and we're just collapsing it to these three right here. So that means my new psi is now just these three terms, because the L equals 0 case got bumped out right here. So all we get is minus I over this, minus I over 3 square root of 2 psi 211 plus 1 all over 3 square root of 2 psi 21 minus 1 plus the square root of 7 over 3 square root of 2 psi 210. Now, I can't just, now if I just wanted to get what's the probability of getting L equals 0, that would just be these two, it can't just be that squared. The reason why is because we're not normalized. By taking out that one term, we're not normal, we have to renormalize it right here. So what do? We put in a factor right here. I don't know, let's just call it A. We just got to normalize it again right there. And so this squared, this times its complex conjugate, which is A squared over 9 times 2, that's 18, plus A squared over 18, plus 7A squared over 18, that should equal 1. Well, this is 9/18. So So this is equal to 9a squared over 18, or a squared over 2, or a equals the square root of 2. So I need to put that square root of 2 up in there, so to renormalize it. So psi, if I put in the square root of 2, the square root of 2's drop out, and we get minus I all over 3, psi 2, 1, 1. If we put in the square root of 2 there, it cancels that. We just get plus 1/3. Psi 2, 1, minus 1. And then this one we get plus the square root of 7 all over 3. That's it. Psi 2, 1, 0. Just to make sure it's normalized, this squared is 1/9. This is 1/9. And this is 7/9. Adding them together, you get 9/9, which is 1. So we renormalized it. And now we ask, what's the probability of getting L sub z equal to 1? L sub z equal to 0, or m sub L equal to 0? It would just be this term squared, since now it's all normalized. So that would just be what? 7/9. That would be the probability. 7/9. Okay. See if that's so we can, by putting any function we have right here in terms of our, remember these psi 2, 1, psi 1, 0, and so on, they're all already normalized. So these guys were already normalized. So that means I just had to make sure that everything out in front of it was then normalized right here. And it's easy to find the expectation or average is just the probability times the value. Probability times the value, and just sum them up. Okay, and so now we can look at mixed states and so on right here. So on the next one, we'll start to include the spin back into it, the stuff that we had at the very beginning. So now we already know where the coin is, and we already figured out whether it was heads or tails. That was our spin. And then the next, we'll just combine the two. Okay.